Hi, I'll be talking about improved rate for non-malleable codes and time lock puzzles. I'm Cody Freitag, and this is joint work with Ilan Komargatsky, Manu Kondopaneni, and Jad Sobek. I want to start by defining what I mean by an encoding scheme. So this is a pair of algorithms, ENC and DEC, that ENC kind of encodes a message into some code word C that then can be decoded by the function DEC to get the original message M back. And so I'm going to think about randomized potentially encodings. So I'm thinking encoding is kind of a function that could use some randomness in order to generate the code word C that can then be decoded. So what does decoding give us, and what does this encoding and decoding process give us? Well, we want some sort of security notion where if someone kind of comes and mauls or corrupts the code word C in some way, resulting in some other code word tilde C, it should decode and get something that's still useful. So for example, in the classic example of error correction, we could consider mauling functions M that come from some class C. And the goal here is to actually require that we'll recover the original message M through the corrupted code word tilde C. However, in this work, we'll focus on the property of non-malleability for a certain class C. So here the idea is that the code word will be mauled in some way, and our goal is that the resulting message M tilde will be unrelated to M. As long as the mauler did something, otherwise we could detect if it didn't do anything and the mauled code word is just the same. But in any other case, our goal is to show that M tilde is completely unrelated to M. And the idea is that compared to, say, error correction, maybe non-malleability can allow for a broader class of programs or mauling functions, um, as long as this mauler can't compute the decode function, which we'll talk about in a bit. So the main focus of this work is actually on a variant known as non-malleable time lock puzzles. Those is the main motivation we're considering. And this imposes some additional requirements on the efficiency of these various algorithms. So one, we're going to have kind of some time-bound t that's going to denote the depth or essentially the running time of the decoding algorithm. And then we're going to require encoding to be much more efficient and run in depth that's much less than this time-bound t. And we're also going to require non-malleability for the class of maulers that run in some polynomial yet smaller than this time-bound t. And again, you should think of this mauling function as being something that can't compute dec. So this is why the depth is less than t, even though it could still be some polynomial function, because otherwise you could have some attacks where, say, you decode the code word C, maybe you can modify the message a little bit and then re-encode, and that would clearly break non-malleability because you'd have an output M tilde from this experiment that's related to M in some non-trivial way. All right. So why do we study these objects? What's been the main application for these non-malleable time lock puzzles? Well, they've been used kind of in interesting ways to generate distributed randomness. So these are protocols between two parties, Alice and Bob, where they interact over some number of rounds. They use their own internal randomness, and their goal at the end of the day is to output some random string. And the point is this string should be random, even if one of the parties, say Alice, is malicious and deviates from the protocol in some way, trying to bias the output. Now, it's been known since 1986, the seminal results of Cleve, that it's impossible to base a protocol of this form to get unbiased randomness based on any kind of standard polynomial time falsifiable assumption. However, Bonet and Noor introduced this framework using kind of timed primitives, showing that from fine-grained assumptions, kind of underlying these time lock puzzles, we can actually achieve this sort of tools and actually bypass Cleve's barrier. And so what does that look like? Well, the idea here is both Alice and Bob are going to use a time lock puzzle to encode some individual random string, R sub A and R sub B, resulting in codes C sub A and C sub B. And kind of you can think of this as a symmetric protocol. Either player could send their encoding first. Then at the end of the day, the random string R output by the protocol will be the decoding of each of the respective values XORed together. And so it turns out that this protocol, the simple protocol for generating randomness, will be unbiased if kind of the wall clock time in between the two messages being sent, kind of you can think of this as some representation of depth, is less than the time pound t needed for decoding. And additionally, we require that this enc and dec functions form this non-malleable time lock puzzle. So if it has this non-malleable guarantee and you can kind of constrain these messages to be sent in some small time window less than the time to decode, then it turns out that this string R will be unbiased. And so the goal of our work is to study this object, these non-malleable time lock puzzles, in order to kind of optimize the communication of these sort of distributed randomness protocols. So our kind of motivating goals are to minimize communication here, and we're going to do this by trying to improve the rates of these encoding algorithms. Where here, rate is kind of a way to measure the length of these encodings, which is defined as kind of the ratio between the message length to the corresponding code length, kind of as you asymptotically take the message length to be infinitely large. Okay, so let's look at one general template to improve rates. So we're going to kind of use this as kind of a simple example that maybe you would come up with, and we're going to see kind of what goes wrong and kind of what this unveils as we look at this specific example. So our goal here is given a rate 1 over poly encoding enc prime, we're going to use this to build a rate 1 almost optimally efficient in terms of length encoding enc. And so the construction will be as follows. So it follows this kind of key encapsulation mechanism idea where to encode a message M, you're going to use the underlying encoding to first encode a seed for a PRG as well as some hash of a message. And then we're going to concatenate this with kind of the expanded PRG used to mask the message. So I'll call the first part of this encoding corresponding to the underlying encoding enc prime, I'll call the C prime. And I'll call the second part that kind of masks the message as the pad. Then to decode, you kind of would do what you'd naturally expect, where you can decode the inner encoding. This gives you the seed S for the PRG. We can use the seed S to unmask the message M, and then verify that the message we get kind of matches the hash from the underlying encoding. And so what's nice about this construction is that it's rate 1, namely the size of the seed and the hash of the message, we can kind of make essentially independent of the message length. So all of the kind of polynomial overheads from enc prime are applied to something independent of the message length. And then the pad itself is just the exact size of the message. It's just a one-time pad, so it doesn't increase the length at all. And so overall, you get something that, as m grows to infinity, is exactly the same length as the message m, with some additive overhead that's independent of m. And so intuitively, it looks like this should be non-malleable. The kind of intuition is that, say the underlying code is non-malleable, then if you change the first part C prime at all, then this should kind of result in a later code that should kind of, at least the value S is unrelated to the previous value S. And so this should kind of lose all information about the underlying message M. At the same time, if you don't mall the C prime part and you only mall the pad, well, this means that the hash value h of m hasn't changed, but you've somehow come up with a new message m prime that should hash to the same value for decoding to be successful. So this results in a collision in this hash function. And so we're going to kind of use tools from cryptography to say like, okay, if h is collision resistant, we can rule out these sort of attacks. And so in this sense, it says kind of whatever part of this code you're mauling, it shouldn't lead to a successful attack. And so it should be non-malleable. It turns out, somewhat surprisingly, that this intuition is misleading. And what we're able to show is that one, it turns out that non-malleability is insufficient to actually give a reduction from the non-malleability of enc to the non-malleability of enc prime. And this isn't some weird bug in the security analysis. Indeed, we're able to show an explicit mauling attack on this construction when applying this to encodings that are time lock puzzles. So that means they have kind of a very efficient encoding faster than the decoding time. And so the main conceptual contribution of this work is a new notion of non-malleability, at least that we kind of formally explore for the first time, called CCA hiding. And what I want you to take away from this is that this is kind of a composition-friendly variant of non-malleability. So CCA kind of follows the nomenclature from, say, CCA encryption or CCA commitments, where there it's chosen ciphertext attack or chosen commitment attack. And here CCA we're using to refer to chosen code attacks. So let me next kind of formalize how we define non-malleability and use that to compare this kind of new notion of CCA hiding. So the way we formalize these notions is via an indistinguishability game. So we're going to look at pairs of messages, M0 and M1, and we're going to select a message at random by taking a random bit B from either 0 or 1. And then the experiment will look as follows. We'll take the message M sub B, so corresponding to the bit B that we chose. We'll encode this message using the enc function, get some code word C, and we'll feed this into a bounded mauling adversary, which will denote M. And by bounded, again, I just mean at a very high level, it can't compute the dec function at a minimum. Or it comes from some general class C that you could parameterize your construction by. Okay, so what does this M do? It produces some mauled code word C tilde. We'll run this through the decoding algorithm. We'll get back M tilde, and then we'll feed this M tilde to a distinguisher. The idea being that this distinguisher shouldn't be able to distinguish whether we started with M sub 0 or M sub 1. And so the distinguisher's goal is then to output a bit B prime, trying to guess what the original random bit B was. And kind of modeling the typical notion of computational indistinguishability, we're going to allow this distinguisher to run an arbitrary polynomial time. Namely, it could even compute the efficient decoding function dec that's only guaranteed to have some depth, which is some polynomial time-bound t. So then at the end of the day, what we want to ensure is that the probability the distinguisher wins in this experiment, the probability that B prime equals B, should be not much better than just guessing. So it shouldn't be better than 1/2 plus negligible. And I want to just emphasize briefly that here we're considering kind of cryptographic assumptions where we're allowing ourselves to assume things like collision resistance and other typical cryptographic assumptions. This is in contrast to a related work that's considered kind of complexity theoretic constructions, where here usually you're only able to get 1 over polysecurity. So here, also for our applications to generating distributed randomness, we really care about getting kind of negligible security. And for that reason, we're allowing ourselves sort of cryptographic style assumptions as well. Okay, so that's how we formalize non-malleability. How do we now compare this to this notion of CCA hiding? So the beginning is kind of a similar setup. We take our random message M sub B, we're going to encode it to get some code word C, and we're going to feed this into now a bounded distinguisher. So we're going to kind of, it looks like we're kind of getting rid of the Mahler in the middle, but we're going to modify things a little bit as follows. We're going to give this distinguisher kind of oracle access to the decoding function. So it's going to be able to decode anything that's different than the input code it received. Then from here, we're just going to directly have it output the bit B prime, trying to guess the original bit B from the experiment. And so kind of we've, in some sense, kind of squished the Mahler and the distinguisher into one guy, this one bounded distinguisher, who alone can't compute things like dec, and doesn't have the resources to compute a function like dec. However, we give it oracle access to this decoding function as long as it's on an input other than the code word it receives as input. Okay, so how do these two notions compare? Well, one, you should think that this distinguisher in the non-malleability game, it can run in polynomial time, but at the same time, it's information constrained in that it only sees the message M tilde, and it doesn't actually ever get to see the code word C. On the other hand, in the CCA hiding game, the bounded distinguisher is given kind of adaptive queries to the decoding oracle. However, it's kind of restricted in that it can't run polynomial time and computations other than kind of explicitly making an oracle call to the decoding function. And so it turns out, and kind of what we want to emphasize in our work, is that the CCA hiding notion is useful because in reductions, this gives a way to argue about reductions that can query the decoding function. Kind of it still gives some guarantees in this bounded setting when you can make calls to this decoding function. And so I want to give an example of this with our first result. So this is the exact same kind of transformation we saw before. Kind of one of the simplest things you could hope would be kind of non-malleable in general. And what we show in our work is that if the underlying function satisfies this notion of CCA hiding, then the resulting encoding function enc is both rate 1, as we argued before, and also satisfies the CCA hiding notion. And in addition, I'll just note that we prove that previous constructions of non-malleable time lock puzzles also satisfy the CCA hiding property. So these are previous puzzles that kind of have bad and inefficient rate. And so this gives a generic way to at least boost them to rate 1 in a way that satisfies CCA hiding from the same assumptions. And so now I want to go a little bit into detail of how we actually show CCA hiding in this construction to kind of show where this notion is useful for composition. And so kind of this is the goal, this is the experiment we have on the left. And in the real experiment, the encoding kind of has this form. It has these two parts, C prime and pad. And again, our goal is to argue that for this real experiment, the probability that the distinguisher can come up with a B prime that equals B should be no better essentially than just guessing. So the way we're going to argue this is by a hybrid experiment. So in this hybrid experiment, we're essentially going to replace all of the inner part of the encoding enc prime used to generate C. We're going to replace this just with all zeros, kind of remove the seed S and the hash of the message M sub B, and instead just replace it with dummy values of zeros. And so what our first goal is, kind of towards arguing that the probability B prime equals B in the real experiment is a half, we're going to show that the probability B prime equals B is roughly the same in both the real experiment and this hybrid experiment. Okay, so how do we do this? Now, the point is that kind of the bounded distinguisher, without making queries to this decoding function, it shouldn't be able to distinguish M sub 0 versus M sub 1 just based on kind of hiding of the underlying encoding scheme. So then it turns out all we need to do is try to kind of show that we can simulate the queries and that the queries that we simulate are kind of indistinguishable between the real and the hybrid experiments. So let's look at a particular query, kind of the C tilde value, which consists of two parts, the kind of what I'll call C tilde prime and the pad tilde part of the mauled encoding. And we're going to do a case analysis based on what this query looks like. So first, kind of if this query was just copied from the original code, meaning C tilde prime equals C prime and pad tilde equals pad, then because we kind of disallow queries of these forms, we can simply reject and we can perfectly simulate such queries because they're kind of not allowed by the setup of the experiment. Okay, so if it can't be the case that both of them are equal, what if the C tilde prime equals C prime? So the first parts are equal, but say the pads are different. Well, here, kind of as we mentioned before, it suffices to kind of just output bot in this case, because if the adversary is able to kind of come up with something that's valid here, then that would correspond to actually finding a collision in the hash function h. And so, assuming that the hash function is collision resistant, this event should happen with negligible probability, so it doesn't affect our simulation if we just kind of output bot in these situations. Now, in the last case, the kind of last events that's possible, it must be the case that the C prime part was actually modeled and modified in some way. And it turns out in this case, we now have the underlying code has been modified. So this gives us a way to actually reduce to CCA hiding of the underlying code inc prime by querying dec prime on this modified value C tilde prime. And so really to make this reduction go through, we need this ability to query this dec prime oracle. And that's really where the benefits of the CCA hiding notion come into play. And so now that we've gone through this case analysis, in each case to simulate the queries, we're able to show that the probability that B prime equals B is kind of indistinguishable between the real experiment and the hybrid experiment. And then it's not too hard to show that the probability B prime equals B in the hybrid experiment is essentially 1/2 because this PRG value is essentially indistinguishable from random, which hides all information about M sub B and hence B. And so this is how we show that kind of the probability of succeeding for any bounded distinguisher in the real experiment is essentially half plus some negligible amount. So to recap, what we showed is we showed how to use this CCA hiding notion for the underlying encoding inc prime to then achieve the same CCA hiding notion for this rate 1 construction inc. And I want to mention that it's not just our analysis that prohibits us from showing non-malleability of this construction. And in fact, we are able to give an explicit mauling attack on this construction. So the question then is, okay, we can't get all the way to non-malleability, which we require for our applications to distributed randomness. So can we come up with other sort of constructions for which we can show non-malleability? So that brings us to our second result, where we give a similar sort of transformation, where if we start with something that's CCA hiding and is a time lock puzzle, then we're able to construct not necessarily rate 1, but a rate 1/2 non-malleable time lock puzzle. But unfortunately here we have to rely on stronger kind of idealized model using random oracles. So I just want to mention the construction looks very similar. I won't go into great detail kind of motivating piece by piece, but I'll just show some of the diffs between the previous construction and this construction for this theorem. So first, this hash the message M, we now have to randomize it in a way. So instead of being a deterministic hash of the message M, we're using this randomness row to kind of randomness and kind of make it look like a non-interactive commitment. Second, we need to append this random string R that's the same length as the message M. This is what makes it the construction rate 1/2 instead of rate 1. And lastly, we feed, in addition to S, the string R into the PRG, and we require some stronger properties of both the hash and the PRG, kind of leveraging some additional properties of the random oracle. And so it'd be a really interesting open question. Can we actually identify weaker notions from the random oracle to instantiate this or a similar sort of approach? But overall, this gives kind of a heuristic construction for at least an improved non-malleable time lock puzzle with rate 1/2 versus rate 1 over poly. For our third result, we show a direct construction of a rate 1 code that is non-malleable for bounded polynomial depth, say less than the depth of decoding, which is some value t. And again, this construction is direct, but in the random oracle model. And I'll note here we're saying a non-malleable code and not a time lock puzzle because this construction has encoding that runs in the depth t, the same as decoding, even though non-malleability is for depth only less than t. And I would just want to briefly mention that the fact that the encoding is slower and runs in depth t is how we avoid the mauling attack on our first construction. So just to conclude, I want to first recap our main results. We first show a rate 1 compiler for CCA hiding, kind of taking anything that's CCA hiding with a very low rate, 1 over poly rate, boosting it to rate 1. And this compiler only assumes collision-resistant hashing. We then give a rate 1/2 version of this compiler in the random oracle model that boosts all the way to non-malleability from CCA hiding. And lastly, we give a rate one construction directly of a non-malleable code with kind of slower encoding compared to time lock puzzles, also in the random oracle model. Now I want to conclude just with some open questions. One is, can we get rate one non-malleable time lock puzzles, even allowing for random oracles? Second, can we get even constant rate non-malleable codes in the plane model? And last, I really think this notion of CCA hiding is potentially interesting for other composition applications. And so I'm curious to kind of explore more applications of the CCA hiding notion. So thanks for your time.